Hi everyone, I'm Nicolas Bonfanti, he's Matteo Pacciani, and we work in Helioswitch, a small Italian company. We came here from Italy, and we do mostly forecast for the energy markets, mostly on the demand side and also on renewables. Since we use Apache Beam with BigQuery as our main heavy lifter for data processing and in general everything end-to-end from the raw data given by the authority to the forecast that we give to our customers. I am a co-founder of the company, and Matteo here is a data engineer and the most expert in that field in Apache Beam. He's laughing, but that's true. So that's us. Helioswitch is the company, and this is from taming energy market data to hyperparameter hunting at scale with Apache Beam and BigQuery. So, a presentation already done, nothing to say more. As you can see, we're a very small company. We are 25% of the personnel is here right now. So, let's start. We're going to start with the needs. Basically, why we are doing this and why it has value. What are the solutions? Why we are using BigQuery and Apache Beam, and then the questions. First of all, who are our customers? They are the balancing responsible parties. These are all the legal entities that produce and buy energy and operate on the energy exchange. They hold contracts with a transmission system operator, and they must obey the regulator rules. These are customers. We are a business-to-business company. Let's skip it. And why is forecast needed? A lot of the energy market is characterized by being non-dispatchable. Basically, solar, wind, hydro runoff river cannot be planned, but must be forecasted using mostly weather data. And almost all demand is not planned, cannot be planned. The customers are not going to send them the plans for tomorrow. That's true for the small, like the domestic one, but that's also true for the big industrial one. In Italy, at least, it's not common to propagate information about the planned demand in the future, so everything must be forecasted. Why is forecasting variable? Basically, almost all the market operates in the day ahead time frame that forms prices in an auction. Everything that is mismatched from the day ahead on the real time is paid on another market that is characterized by being with a higher risk and a higher cost generally. So forecasts on the energy market in Italy have this direct and very quantifiable value. So this is why forecasts are needed. Why is data warehouse scalability needed? That's because in Italy, in these years, we are switching from an aggregate system with very few cores already aggregated by zone to a meter by meter 15 minutes resolution. So a lot of the existing data warehouse system, the legacy ones of our customers, starting to fail and undergo a lot of stress. So these are a few numbers. We handle more than 2 million of meter data. This is almost 6% of the Italian aggregate demand. This presentation is going to focus on the demand side. Let's start with downloading the data.
Okay. Take it over from here. So hi everybody. For downloading the data, what we do is to use like a WebDAV protocol that is used to actually download the files from Nextcloud servers. That is what the Italian authority uses to store all the files. And like basically it is a lot of like millions of XML files, and they are organized in a file system-like structure. So we use data flow pipelines like we use two pipelines, but one is the main one, and the other one is just an error correction pipeline to download these files to Google Cloud Storage buckets. And at the same time, we verify the integrity and the completeness of the data transfer. So as I was saying, the main downloading pipeline is the one in charge of the entire 90% of the download process, and starts with reading from a logs table. And that table is populated by that same pipeline in a later stage. And like after reading this logs table, it starts exploring the folder structure of the file system by some like list calls. And like as soon as it finishes, it starts extracting those relevant metadata, and then proceeds to download and upload files to the bucket. So like, as you can see, there are two branches at this point, and in parallel, we process and save the logs about those folders and metadata, and we store them in a BigQuery table. And at the end, we merge these two branches and wait for them to finish and log the status of the entire pipeline. So the error correction one just starts from the logs, like the error logs, and then like fix them up if something went wrong. And then does basically the same. So like we use many components, but like among the most important ones, I would mention the read from BigQuery, of course, because like it's where it starts. And then like we use batch elements because we found it particularly useful, because the servers we're connecting to are actually not that easy to handle. I mean, sometimes they can be slow. So we found out that this component helps us dynamically adjust the number of simultaneous connections, and it uses a heuristic, so we're fine with it. And yeah, so it's a nice trick we found out. Then I would say, yeah, okay, after the download phase, when we have that data, we have to parse it, and we use another data flow pipeline to do that reads those files from the Google Cloud Storage bucket and starts converting them to JSON-like files and structures. And then what happens is we prefer an ELT approach, because like we want to stick to the original structure of the files and process them later on in our pipelines. So at the same time, we decided to use like the Google Cloud Storage file system to log all of these operations. And like we just move the files around in dedicated directories, for example, to track some exceptions that could occur during the process. So the pipeline is quite straightforward, and yeah, like just matches all the relevant files from the folders on Google Cloud Storage, and then parses all the files according to the expected table schema. So like the main part of this pipeline is the XML parser, and yeah, like the problem of this pipeline is just like the problem of an ELT approach, that because of this we have the main downside, that is a messy structure of the original data that propagates to the unprocessed table. So, but this was a design choice, and like we are still fine with it, and we don't regret it. So for the next process.
So from this point to the one you're seeing in this slide, there is a lot of processing, but it's all done in BigQuery, and we are not talking about that now. And we reach a point in which we have a nicely organized data set with all the timestamp that you need point of delivery IDs. These are the single curves, all the location, the properties, the total demand, the weather, and the calendar data. When doing forecast, we can work with this data, with the fine data, pod by pod data, or aggregate it. In this example, we are going to aggregate it in the city aggregation with respect to the geography and for voltage. For example, a single key in this case could be Milan, the 220 volt categories, all aggregated. Once we do this, we start with Apache Beam. We have our data entries, and what we do is we aggregate, in our case, by city and voltage. And the aggregation operation is creating a data frame. Why are we doing this? We are not doing a single big training or inference of a big model and distributing it with Beam. But we have a lot of small models. They could go from tens in a very coarsely aggregated case to millions in a pod-by-pod basis. And we are scaling over that. So we have our city, our voltage, and a data frame of data. We co-group it with the existing machine learning model that are tagged with city and voltage, and start doing different operations. The one can be inference. Basically, we take past demand, future weather forecasted, obviously, future calendar data, and 1 to 4 times a day, we, through an inference process, distributed inference, we obtain future demand. We could take just 1 year of data, and once a week do a training. We take existing machine learning models, we update them with the new data, and upload it back. Or we can do a search. Basically, is a meta training. We are training over the hyperparameters of the model. It's very similar, but it generates also backtest data, and needs more data than a normal training generally. Let's go a little bit deeper with the inference. Basically, this is the pipeline. It's kind of simple. On one side of the branch, we take all the BigQuery data, aggregated in this case for city and voltage. On the other one, we take the from Google Cloud Storage the models, serialized with joblib. We merge them, and then we just run, let's say, in this case, they could be 10,000, 20,000 models. We distribute over them, and we do inference. Why do we need the past demand with the future regressors? This is because our model are a mix of autoregressive and regressive. So we use all the weather data and the calendar data as regressor, and we adjust all the forecasts using the most recent available demand data. The other step is training. Training is very similar. It's the same pipeline, but due to different parameterization in the first step, it spawns a different DAG. And what we are doing here is we are downloading the existing model, the historic data, and doing another training. The output here is an upload of a model and not of new inference data. And this model allows to model mostly anything on this kind of data, from the autoregressive components like single pods, or in this case city with lower than expected demand, or thermal inertia, which is coupling of weather and autoregressive components. Then searching. In this case, in this diagram, we are making an example with the search, with a search that does not download existing model, but spawns model from zeros. And what this search does is this. We download hyperparameter distribution. This means that our hyperparameters of the model are characterized by not being a single value, but sample from a distribution. And we do different stages, sequential stages. They're called trials. And each trial has a lot of trainings and a lot of evaluation. It's a cross-validation doing sequentially because it's a time series. It has a strong causality in one direction. We look at the evaluation, and we change the hyperparameter distribution, and we go to the next step. We sample again, we do a trial again, and we update the distribution. And we repeat this process a lot of times in order to change the distribution. This is basically a Bayesian optimization over the hyperparameter. It's an optimization of an optimizer. And we do a final training. So how is Beam used? We have the iteration within the training and the trainings within the trial. They are parallelized in the same worker. We have the trials within the optimization that now are serial. They could potentially be distributed with Beam. We have the optimization over all the models that is distributed with Beam. Basically, the main axis of distribution here is the fact that we have thousands, tens of thousands of models, and we want to do this search in a parallel fashion. And then there is the monthly update of the model that is intrinsically serial because of time. And what now? We reach for the forecast of Italian demand state-of-the-art errors, but there are ways to improve. The first one, I already talked about this, is distributing over the trials. It's a little bit trickier because different workers are going to work on and update the same distribution at the same time. It's not as trivial as distributing different models as we do right now. Or we can combine all the information about all the distribution across all the models with their metadata and do a zero-shot hyperparameter learner. Or we can also switch to a sort of big single hyperparameter distribution that can be conditioned over the metadata. So basically, we don't have like the distribution for Milan, the distribution for Rome, the distribution for another place, but we have a single big distribution that can be interpreted using the geographic location, for example, as an input. So this is it. Thanks.